So far, we've described distributions with words spread out, leans left. This video puts numbers on that, and I'm going to be honest about how much to trust two of them, because the standard rule you'll read online will mislead you badly on a file this size. Descriptives with age and education. Education should already be set to continuous from video 1 if yours still shows the nominal icon. Double-click the header and fix that now, or none of this will work. In the statistics section, minimum and maximum under dispersion, then skewness and kurtosis grouped under distribution. Easy 2 first. Age runs 18 to 89. 18 by design, the survey only interviews adults. Education runs 0 to 20. 0 should make you stop. 0 years of formal education is possible, but it's also exactly what a data entry error or an unflagged missing code looks like. Here, it's genuine. The point is that checking minimum and maximum takes 4 seconds and catches a huge share of what goes wrong. Do it every time before anything else. Skewness. Age is 0.435, and underneath it, Jamovi gives the standard error 0.0 to 1. The sign gives direction. Positive means the tail stretches right, a pileup at the low end, a few high values trailing off. Negative means the tail runs left. Education is minus 0.38, which fits because most people cluster at 12 and 16 years and the tail runs down toward very little schooling. Now, the rule you'll find everywhere. Divide skewness by its standard error, and if the ratio beats about 2, call it meaningfully skewed. Let's try it. Age, 0.435 divided by 0.01 is 43. 43. And I want you to be suspicious of that. Here's why. That standard error shrinks as the sample grows, and we have 60,000 people, so it's tiny, which means almost any departure from perfect symmetry clears the bar. A skewness of 0.43 is a mildly skewed distribution. You'd barely see it by eye. The ratio says 43. This is a preview of something that will come up over and over. With a large enough sample, trivial effects become statistically significant. Significant doesn't mean large, and it doesn't mean important. It means detectable. So pair that rule with one that doesn't care how big your sample is. The quick gauge I want you using in this course. If skewness falls between -3 and +3, treat the distribution as close enough to normal to go ahead. Same range for kurtosis. It's a rule of thumb, not a test, and that is exactly why it still works at 60,000 cases. By that gauge, age at 0.435 isn't remotely close to a problem. Neither is education at -0.38. The ratio said 43. The rule of thumb says relax. When those two disagree in a large sample, go with the rule of thumb. The ratio isn't lying to you, it's answering a question you didn't ask. It asks, could this skew be 0 in the population? And with 60,000 people, the answer is almost always no. What you actually need to know is this skew big enough to distort my analysis? And that's a question about the size of the number, not its significance. Kurtosis, same logic, quickly. It describes how much sits in the peak versus the tails. Positive is a sharper peak and heavier tails. Negative is flatter. Age is -0.75, which fits a broad, even spread of adults across 7 decades. Education is +1.07, which also fits because 18,000 people in this file report exactly 12 years. One number, one enormous spike. And the same gauge applies. -3 to +3, -0.7 to 5, and +1.07 are both well inside it. Kurtosis has its own standard error sitting underneath it too, and dividing by it would give you another enormous number for the same reason. So don't look at the size of the statistic. So, 4 numbers, 1 verdict. Both variables are shaped a little differently from a perfect normal curve, and neither is shaped differently enough to change what you do next. Both of those are telling you something you could have seen in a picture, which is the whole point of the next video. Numbers and pictures should tell the same story. When they disagree, believe the picture and go find out why. And these aren't decorative. A badly skewed distribution means the mean is getting dragged by outliers, and the median may describe your data better. When we reach tests, is this roughly normal, becomes a formal assumption you have to check. This is where that starts.